Okay, welcome everybody. My name is Professor Pablo Moscato, and I am with the School of Electrical Engineering and Computing in Newcastle, Australia. So we are going to talk about analytic continued fractions and their applications for regression. So the basic of our method goes all the way back to a result proved by Leonhard Euler in 1748. In which he proved that the sum of products can be written as a continued fraction. So this result motivated us to look at a new way to represent an unknown target function for our problem of interest by representing it as a continued fraction. It is a very powerful representation, and it allows you to fit very well very well-known mathematical special functions. And I invite you to have a look, for example, to the Wikipedia article about this. So in this case, we decided that our unknown continued fraction will be of this form. We will have each one of these G1, G2, G3, they are all linear forms. So there will be coefficients that we need to adapt through our learning procedure, and variables that we will need in a multivariate setting. We will need to select which are the variables that will appear, and constants. So we will have these linear functions all for H and G. So the problem that we have, the problem of identifying the unknown target function, reduces to solve a nonlinear optimization problem, which is defined by the use of this analytic continued fraction representation. So for multivariate setting, this requires an identification of a subset of the variables that are given to you as an input. We are using several different metrics to do the learning, but we are going to present results here related to the mean square error, as it is popularly used for several applications. So here is an example that you can see the gamma function, which is a difficult function to approximate. But we will see that if we increase the so-called depth of our representation, so here are results of depth 2, depth 4, and depth 6, we will see that at depth 2, basically having two ratios considered in the infinite sequence, we are doing a pretty good job, but we are able to refine in level 4, and we are able to refine it even better in depth 6. You know that for problems that involve noise, increasing the power of the representation of the training dataset may eventually lead to overfitting and a mediocre generalization. So we need to investigate the depth of the representation, and whether we will need eventually to decide if we are going to have it fixed or dynamically change it during the search optimization process. In 2019, we have a previous result at the IEEE Conference on Evolutionary Computation, where we fixed the value of the representation to 3. And we did that in order to have a baseline study and to characterize what is the approach when we have a limited depth performance. Note that if we search with a representation with depth equals 0, this means that our techniques basically corresponds to approximating the unknown function with a linear function. And since in general, we have to select a variable, a set of variables, we have a mixed combinatorial optimization plus linear regression problem if we just approximate with the first function. So our representation naturally includes linear regression models for any value of depth greater than 0, and it will be interesting to see if greater values of depth leads to better representation of mathematical functions. So for example, when you reach depth equal 1, your approximation is now the ratio of polynomials, P2 or Q2, given by this expression. And in general, the depth equal D is going to be the ratio of two polynomials, which will be on the variable X. And there are some ways of representing this with matrices that lead to speed ups in terms of the ability to do it on parallel computers. So we are using memetic algorithms, which is a technique that has been around for 30 years. And we have been recently applied this technique for exactly these problems in the previously cited paper with Sun that initiated the field, and together with Haque as well, in 2019, which is a preprint that is available on arXiv. So I would recommend you to have a look at that because it's the most comprehensive discussion about the whole method and a review of applications in several datasets. We normalize the data. The objective of normalization of the data is to a pre-processing step, which is useful in machine learning, of course, and we are using min-max normalization, which is traditional in the field as well. The memetic algorithm is well described in the arXiv of paper, and we are using depth equal 4. Initially it was depth equal 3, but we are using depth equal 4 also in this paper. And we are doing it to try to have a baseline comparison of the results of this paper with what we have in the previous one. We are using also k-fold cross-validation, but in this one we decided to use leave one out cross-validation. And the reason is that in this data set, the largest one of the data sets has only 109 samples, and most of them have less than 50 samples. So it is reasonable to adopt a leave one out cross-validation for the whole data set and be consistent in that way. So details of the memetic algorithms are given in the paper and also in the arXiv, and I will recommend you to go and see them there because it probably will take some time until I explain all in detail, but it's an evolutionary optimization technique. We compare with several algorithms available on the ScienceKit machine learning database, and they correspond to adaptive boosting, gradient boosting, kernel ridge, several variants of linear regression, multi-layer perceptrons, random forest regression, stochastic gradient descent, and the very famous now extreme gradient boosting approach. So the dataset contains 352 bivariate numeric datasets that were collected by Schaeffer. The dataset is now on the public domain, and it's separated in cases. Schaeffer used it initially by separating the cases into training cases and the test cases. So in this use, we differ with Schaeffer, in which we are using leave one out cross-validation. So we used a high-performance computing grid from the University of Newcastle. Details are given in the paper. So in the first part of the paper, we look at the performance on the same datasets that have been previously studied in our paper on the IEEE Conference on Evolutionary Computation of 2019. Scores are not directly comparable because now they are on a normalized dataset, but in this case, we want to see our method in comparison with the different methods that were in the ScienceKit learning, which is all these machine learning techniques. And we wanted to see how the value of depth equal 4 will do in that case. So it was an initial testing of the waters to see how we will do. And then we apply it to the 352 functions dataset. That is the core of this paper. We see here the performance in the training dataset. So this is our method, and it shows that in training we have an average which is much better than all the other techniques. And the interesting news is now that in testing, the results are significantly better for our method in comparison with all the other methods. So we will see also that in terms of the ranking of our method, if we look at it like this, the performance is even more impressive because in 350 out of 352 datasets, it was the top ranked method in fitting the data. So it was very, very good in training performance. And also in generalization, so here we have our median, and you will see this why, because our median value was most of the time, it was the first in testing. So in fact, 192 times our algorithm was ranking the first, 54% of the time for the testing performance. The closest performance algorithm is linear regression in this case. 97 times was first in testing, but it never became first in training. That was very interesting to know. The results of statistical significance shows that our method, at least in this dataset, perform as linear regression, but you will see, you have seen there that many times it was better in both in training and generalization. So I'll refer you for the paper for all the results in terms of statistical significance. So these two methods, basically, our method and linear regression, were superior to all the other methods of machine learning regression that we have studied. So in 358 datasets that we have studied in this paper, our proposed approach exhibited better performance when compared with most of the approaches. There is something interesting regarding linear regression. At the time that these datasets were created, that was at the beginning of the 20th century, there was a significant work by the physicists of the time of presenting the data in a way that they, when tabulated and shown graphically, a linear trend will clearly appear. So then they will have some way of guessing what will be the right power of the unknown or the target variable. So even if they don't know the unknown law, they will be guessing pretty well the power. So then by taking logarithms, perhaps they were able to fit the straight line pretty well. So in terms of the generalization performance, our proposed method outperformed all the state-of-the-art machine learning algorithms for the median MS score, and it shows the superiority of our method over the state-of-the-art machine learning-based regression methods in terms of generalization performance. So we showed also that the statistical tests show that our method was top and now shared also by the good performance of linear regression, at least in this data set. But if you go to our archive paper, you will see also that in the 94 data sets that we studied from the Penn machine learning database, linear regression, of course, did not perform as well, being the second last performing method. So this also speaks about the robustness of the method of analytic continued fractions that we are proposing within the memetic approach that also helps to perform variable selection when we are dealing with a multivariate formula. So finally, for the conclusions on future work, we would like to include the possibility of introducing new variables, typically like kernel methods of support vector regressions or some other methods that they look at the products of variables, and let then the memetic algorithm search for the best combinations to build models. And as a representation issue, for example, if you want to represent a trigonometric function tangent of x multiplied by x, this is how it is. So clearly, if I have passing a table with only x as a variable, it will be for our current method that we are using linear approximations on each one of these functions, then we will need to include x squared to have a quick approximation to the unknown function. So it's very interesting then that this also links with some of the proposals of the originator of the dataset, Schaeffer, in which he was also interested in looking at creating new variables with different powers of the original variables. So we have also seen by the combined studies of this paper and the other one that I mentioned, that it is in X-Archive, the good performance of boosting algorithms. So this motivates us that in the future we could include boosting within our methodological framework. We haven't done it yet because we want to see how far we can go with the present methodology until we enter to use some of these techniques like bagging or boosting. And in conclusion, putting together, the performance of our memetic algorithm that used analytic continued fractions was compared with many current algorithms for multivariate regression, and this clearly indicates that the approach deserves further investigation. We would like to acknowledge some talks with Marcus Wagner from University of Adelaide that gave us comments on the early version of the manuscript, and you have some references that you can check after the talk. Thank you very much for your attention. I hope to see you soon.